Hey guys, I hope all is well. I was going to just give you a quick homework help video because this one's going to be pretty brief because I've covered most of the problem types that you'll find on this homework. But there's one type that I haven't done in a video yet, and that's going to be related to finding the sample size to achieve either a certain power of a test or a certain probability of a type 2 error. Remember, those are the same thing because those two numbers always add to 1. So if you know the power of the test, you can easily figure out the probability of a type 2 error and vice versa. So this is the last problem in the Chapter 9 assignment. Your numbers might be different. And in fact, as we'll see in a second, my numbers changed between when I checked this problem out and right now when I drew this diagram. But anyway, this number is about an automobile mileage study tested the following hypotheses. The null hypothesis is that mu, the miles per gallon, is greater than or equal to 25 miles per gallon. The alternative is that mu is less than 25 miles per gallon. And then down here they tell us that the true mean is 24. So we're asking, what's the probability that we will pick up the fact that the true mean is less than the null mean in this test? So we basically want to figure out what's the probability that we reject the null hypothesis because they're asking for the power. But really, they're targeting the power. They're telling us we want the power to be 80%. What sample size do we need to achieve that? So let's take a look at, yes, we do need more time. Let's take a look at this diagram I drew. Now, they changed the numbers on me, so in my version of the problem, the null mean was 24 and the true mean was 23. In this version, it's just shifted up by 1. The null mean is 25, the true mean is 24. This actually won't change the numbers in the problem, which is good for you to think about and recognize, because the distance between these two numbers and then the variation, the sigma and the sample size, those things affect my power and my type 2 error. But just 23 and 24, if I shifted those up to 24, 25, 26, 27, that actually wouldn't change any of my numbers as long as the distance between these numbers stayed the same. But just to reiterate, my version of the problem when I drew this was a null mean of 24 and a true mean of 23. In this problem that we're doing right now, they gave us a null mean of 25 and a true mean of 23. So the general diagram is the mu naught, the null mean, and the true mean. It's not always below, but in this problem, the true mean is below the null mean. And that's what's the really important part when you draw the diagram, is getting that ordering right, because that will change the shaded areas. And as you know, that affects our Excel formulas, so that's really what we need to be thinking about. So they tell us in the problem that alpha is 0.02. They also show us a one-tailed test, which is important. So that means I can draw this line here, call that the critical mean. I'm going to reject my null hypothesis if I land to the left of the critical mean. What defines that critical mean? Well, it's the number that divides the null distribution between 98% and 2% alpha. Okay? So that's what we're going to use that information to figure out what the critical mean is. Once we've identified the critical mean, we can say, okay, well, my data is actually coming from the true distribution over here. What is the probability that I land to the left of the critical mean when I pull my data from the true distribution right here? Okay? So that's the power of the test. That's the definition. That area represents the power of the test. And this problem isn't asking us for the power, it's telling us the power is 80%. What sample size do you need to achieve that? Now, notice that the reason that the sample size increases power is what happens to both of these curves as we increase the sample size. Well, we take our sigma, our population standard deviation, and divide by the square root of the sample size to get the spread of these distributions, right? So as our sample size increases, these distributions get tighter around their means. This area gets smaller when that happens, and the green area gets bigger. Or sorry, the green area gets bigger when that happens. The power of the test will get bigger because basically you can imagine this tail being pulled in this direction towards the green area as the sample size increases, which will increase the probability in the green area. Okay, so that's the information we're going to use when we go to Excel here. So I've just filled in some information that they gave us in the problem. They told us that the null mean is 25, that the true mean is 24, alpha is 0.02, and sigma is 3. Now, of course, they do not tell us a sample size because that's the question. Now, the way the book has you do these problems, provides you a formula, and that's fine to use. But I want to use this opportunity to show you a really powerful thing that you can do in Excel. Is if you have a really complicated problem or formula and you have to solve for a number, one way is to use the formula. Another way is to do what's called a numerical solution. So what I'm going to do is I just listed tons of different sample sizes right here. To make this column, I'll just show you how I made it. I just did sample size. And then just, okay, well, the smallest will be 1, or we could do 2. And then once I do that, I say probably the answer is a lot bigger than that. And so notice the powerful thing about Excel is we could drag this down to like 20,000. And then what could we do? We could check what the critical mean are and what the probability of being less than the critical mean, which is going to equal the power for our problem, by the way. And so basically what we're going to do right now is we're just going to sit here and calculate the power for every single one of these sample sizes, and then we're just going to search our spreadsheet for the sample size that provides the power we want. Okay? So let's start by finding the critical mean. So we need to find the number that splits this null distribution. Remember, in your problem, the problem we're working on right now, this is 25. But so it splits this distribution into 0.02 on the left, which is helpful to know, and 0.98 on the right. So that's going to be a norm.inv formula. Okay, and our area to the left is 0.02. The mean that we're taking that from is the null distribution. So I'm going to click on the null mean, and I'm going to lock that by putting $signs around it. There's a shortcut for that. It's Command T on a Mac. I'm not sure what it is on Windows. Now my standard deviation, we're thinking about sample means right now. So standard deviation means standard error. Standard error is sigma divided by the square root of our sample size. I'm going to go ahead and lock. I do want to lock my population standard deviation because I'm going to drag this formula down. I do not want to lock my sample size though, right? Okay, now we can double click this down, and what we see is that the critical mean gets larger as our sample size increases, and that makes sense because as the sample size increases, this red null distribution gets tighter. So we don't have to get as far below 24 to reject this null hypothesis. Or in your case, 25. We don't have to get as far below 25 to reject. If you only have a sample size of 1, you have to land super far away from 25 to reject the null hypothesis. However, if you have a sample size of 1,000, you don't have to land that far away from 25 to reject the null hypothesis, like less than 0.2 below it. So that's how much the sample size affects how far away we have to land to reject the null hypothesis. Now we're going to ask, what's the probability of landing there given we know the true mean? So now we're going to say, what is the probability? Notice I'm using normal distributions for all this because they gave us sigma. Doing power problems is even more complicated using t because the t distribution depends on the sample size, right? A good way to do those types of problems is use this Excel numerical solution type way, and that solves a very complicated formula issue for you. Okay? So norm.dist, we need to figure out the probability of landing to the left of the critical mean. So the left of what number? This number, that's the critical mean. The standard deviation is this again. That should be locked, but divided by the square root of the sample size right here, and then cumulative is true. So we have the x, I forgot the mean, which what's the mean? We're taking this from the true distribution, right? Notice that when I calculated the critical mean, I used the null, because that's based on the null distribution. But when I calculate the probability, I base that on the true distribution, because that's where I'm pulling my data from. And again, sorry that it gave me different numbers. So you should be thinking 24 is true, 25 is null, because they just shifted this when I did this new version of the problem. So we have x right there. We want to land to the left of the critical mean, because right here, this formula is calculating the green area based on the sample size. So for a sample size of 1, the green area is to the left of this critical mean from a distribution centered at the truth, 24, with a standard error of 3 divided by the square root of the sample size. Right there is the sample size in green. And then we always type true, of course, at the end of our norm.dist ones. So that looks like there's about a 4% chance of rejecting the null hypothesis if we only use a sample size of 1. But as we increase our sample size, so I forgot to lock something, it looks like, which is the critical mean right here. Because I don't want, as I drag my formula down, I don't want that number to move. That's why those ones all showed up, is because I didn't lock all of my formulas right. But now we see that as we increase the sample size, and as the critical mean gets closer to the null mean, the probability of rejecting the null hypothesis, or the power of the test, increases. Now I can just search. So this problem wants us to find, recommended if the researcher wants an 80% chance of rejecting the false null. So we can just start scrolling down here. And then we see that 80% occurs. We jump from 79.7 to 80.3-ish right here. So that means to achieve at least 80%, we want this 76 sample size, okay? So let's check that out. Notice that they're just using this formula. Now, for me, and when I look at this, I'm like, man, I should have just used the formula in this case. But also using that formula, I think, is a lot less intuitive than what we just did in Excel. So that's the number one thing that at least I want you to think about and understand this technique. Second, we could imagine applying this technique to much more complicated problems where there's not this nice little formula to deal with. Not only that, but now notice that I have a calculator that calculates power and sample size for me. So if I was like 128, all those are 1 because of this distance now. So I'm going to do 123. Those are a lot bigger now because of the distance between these change. We could change this to a 0.05, which would be more standard, right? That's going to change some things around. Maybe we have a bigger sigma. And now notice I just have a handy calculator that now I can go like, oh, I changed my test. What sample size do I need now to get my 80%? Now I need 94. So now I can quickly, now that I have this spreadsheet that I've saved on my work computer called Power Calculator, I could have one sheet called left-tailed, and then I could make another sheet called right-tailed, and then I would just have a calculator for the rest of my life that calculated these super complicated powers. And I would go sit in my office and pretend to work for like 3 hours, and then I'd come and be like, hey, I figured out the power for that problem. But really, what was I doing that whole time? Watching cat videos. All right, I'll see you guys later.